All right, so hello everyone. I'm Norman Wildberger. We're at the University of New South Wales. Today we are going to talk about paraboloids and their associated quadratic forms. So we're going to be actually studying things a little bit more generally. We're going to look at quadrics in general. And I remind you, these are quadrics in three-dimensional space. And by that we mean basically an equation of degree 2 in x, y, and z. And these are going to be the analogs of conics in 2D, but their theory is much more complicated. So we're going to start by looking at some special ones. So the paraboloids are special kinds of quadrics, perhaps the simplest kind. They're the ones that are given in the form z equals f of x, y, where f is a polynomial, homogeneous polynomial of degree 2. In other words, we're talking about something in the form ax squared plus 2bxy plus cy squared. That's a paraboloid. The z is to be thought of as a function, so we can interpret this as the graph of a quadratic function in the x, y, z space. And, well, there's various possibilities. So the first, simplest kind is something that looks like this. Okay, so that's the first example. Is called an elliptic paraboloid. It has an equation of something formed like z equals x squared over a squared, say, plus y squared over b squared. That would be an example of an elliptic paraboloid. Somewhat less simple to graph is a hyperbolic paraboloid. Which has a equation, well, something like, for example, something in the form x squared over a squared minus y squared over b squared, for example. Or a different kind, or z equals x times y. All right, so let me attempt to try to draw that, although I probably won't succeed very well. So x, y, z. Okay, so let's draw it something like this. Okay, so it's meant to be a kind of saddle shape where it's going through the origin, and it's in fact tangent to the xy plane at the origin. And in one direction it kind of goes up. So for example, if you set that equal to 0, then it will go up. But if you set the other one equal to 0, then it will go down. So it's a parabola in one direction going up and a parabola going down in the other direction. There is a third kind, somewhat more degenerate kind, called a parabolic cylinder. Where we have something like z equals just, say, x squared, or maybe x squared over a squared. So here, there's no condition on y, so y could be anything it wants to be. And in the zx plane, we have a regular parabola. So in the zx plane, we have a parabola that's like this. And y can be anything it wants to, so it can, we can just translate this thing So it's a cylinder. It's like a parabola across a line. Well, in this case, it's open upwards. But if I put a minus sign there, then I could have it opening downwards. And by changing things, I could move it into different positions as well. Okay, so these are examples of paraboloids, and they're particularly important for us because of the following. So our strategy for a surface is, well, we're looking at a surface, we look locally. So for example, we might look at the point 0, 0. And we have some general surface. Then at this particular point, 0, 0, it has perhaps the shape of a graph. So perhaps we have f of xy equals z is some general function of x and y. Perhaps well, a plus bx plus cy plus dx squared plus 2exy plus y squared plus cubic terms gx squared plus x cubed plus hx squared y, and so on. Okay, so a general kind of thing. And we might assume that it goes through the origin, or maybe not. And our strategy is going to be to look at this thing sort of locally. So if we assume that it goes through the origin, well, and that tells us that A is equal to 0. And then the first approximation to this thing is the tangent plane. Which of course then is just this plane which is normal to the vector, well, actually, the way I've written it, BC minus 1. Okay, but the tangent plane will be essentially z equals bx plus cy. That's the first order approximation to the surface. And then the second order approximation is the tangent conic, which will be these linear and quadratic terms together, bx plus cy plus dx squared plus 2exy plus y squared. I should put maybe an f here. All right, so that's the tangent conic, which is the quadratic approximation to the curve. And that's what we're, in fact, really interested in here in this course, as we've seen before. So maybe it's something like this. Okay. All right, so to make life simpler, to understand this in a more simple situation, what we can do is we can look at an even more special case. So the special case when the tangent plane is actually horizontal. All right, in that case, we are just talking about the conic is just dx squared plus 2exy plus fy squared. And then that will be is then a paraboloid. So in the special case, when we're assuming that our surface goes through the origin and has a horizontal tangent plane, then it's essentially given by a paraboloid. And it might be one like this, an elliptic paraboloid, or it might be the more complicated one, like a hyperbolic paraboloid, or it might be a parabolic cylinder. But in any case, our strategy is going to be to understand these paraboloids and to define and study properties of the surface via this associated paraboloid. That's going to be simplest in this case when the paraboloid is straight up and down, but with a little bit of work we'll be able to also deal with a more general case. So it's very analogous to the way we thought about curves, except that we're going up in dimension, so the complexity is a little bit greater. And the paraboloids are just more interesting and more subtle than simple parabola in the one-dimensional case. So let's have a look at one of these paraboloids and let's have a look at the associated quadratic form. All right, so we'll suppose that we have a paraboloid that looks like ax squared plus 2bxy plus cy squared. And the coefficients a, b, and c are some numbers, and their sizes and signs will determine what kind of parabola we have. So associated to this, as we've seen several times in this course, is a matrix. So to this paraboloid we associate a matrix. The matrix, let's call it A, whose entries are A, B, B, and C. This is the associated 2 by 2 symmetric matrix. And in terms of that matrix, we can write down this expression as z equals, well, the vector xy times the matrix A times the vector xy transpose. And this kind of expression is called a quadratic form. In mathematics. And it's a very important kind of thing that comes up in number theory, it comes up in geometry here. It's really intimately connected with metrical structure of all kinds. Okay, so a quadratic form is a very flexible kind of thing that appears in many different contexts. There's also an associated bilinear form. So I'll write that down too. So the associated bilinear form, that's sort of like a dot product. And we might write it as a dot product. So x1, say dot x2, y2 is the same formula, but just with these two vectors being perhaps different. So it's a symmetric bilinear form. Okay, so we have to say a little bit about quadratic forms. We'll say a little bit more about them later in the course, but for now we'll talk about some basic facts about them from linear algebra. So if we think of this thing as a function of x and y, so if x q of xy is xy times this matrix times xy transpose, we can maybe think of it as just VA, V transpose, where V is the vector xy. Then one thing that we can do with this quadratic function is to change coordinates. It's a very popular thing to do to try to simplify the quadratic form, to bring it into a more manageable place. So change of coordinates, what does that involve? Well, it involves a linear transformation. All right, so we're going to linear algebra, and we're thinking about a linear transformation. Say V goes to, these are row vectors, so a general linear transformation might be obtained by multiplying by a matrix M on the right. All right. Now, M should probably be an invertible matrix. So a 2 by 2 invertible matrix. So in that case, we can sort of define a new quadratic form by composing with this transformation. So we can form then a new quadratic form, say Q sub m, whose value at x and y is just v times m times a times v times m transpose. Well, by the matrix properties, this we can write as V, M, A, M transpose V, and we put the brackets like this. Then we see that we have a new matrix from the old matrix, and this new matrix, let's call it B, say, is obtained from the old one by multiplying on the left by M and on the right by M transpose. So the new matrix is B, which is M, A, M transpose. Okay, and this is a way of then getting from one quadratic form, getting another one, and these two quadratic forms are generally called equivalent. So the two quadratic forms, the one we started with, Q, and the new one, QM, are called equivalent. And going back to Fermat, really, and Gauss and Lagrange, one key idea in number theory, for example, is you're given a quadratic form, is to try to change coordinates judiciously so that you have an equivalent but simpler quadratic form. Question? How do we know that B will be symmetric? Well, if you just take the transpose of this, you'll get, the transpose reverses the order. So you'll get M, A transpose times M transpose again. So it's automatically symmetric. All right, so this is a standard thing that we do in the theory of quadratic forms. In number theory, is we change coordinates in this way. In geometry, we're particularly interested in certain geometrically pleasant transformations, which are represented by orthogonal matrix. So particularly pleasant is when this matrix M is itself an orthogonal matrix. What does that mean? Well, it means that M times M transpose equals M transpose times M is the identity matrix. Or another way of putting it, equivalently, when M transpose equals M inverse. So these orthogonal matrices, of course, are intimately connected with geometry because they're associated to linear transformations which preserve the metrical structure. All right? So such transformations preserve our usual metrical structure. So what I mean by that, I mean the standard dot product, we look at the usual dot product or inner product. Say v1 dot v2 equals x1, x2 plus y1, y2, that familiar one. Then that can just be written as v1 times v2 transpose. And then if we have a orthogonal matrix, it'll be the same as v1 m, v2 m transpose if m is orthogonal. So orthogonal matrices preserve the inner product. That's why they're important in geometry. And we're going to see shortly that they're also important when studying these quadratic forms and associated paraboloids. What do orthogonal matrices look like in 2 dimensions? Not too hard to give some examples. So we recall that if we have a matrix M, let's say with coordinates x, y, z, and w, this is an orthogonal matrix. We'll just say orthogonal. Precisely when? Well, the condition that m transpose equals the identity amounts to the condition that the vectors x and y and z and w are perpendicular, and they're both of unit length, and the quadrants of x, y equals the quadrants of z, w equals 1. In other words, x squared plus y squared equals z squared plus w squared equals 1. And geometrically what it means is we're just taking 2 vectors in the unit circle which happen to be perpendicular. Now the standard thing found in most texts is that, for example, you can just write down m as, say, cosine theta, sine theta, let's say. Well, maybe I'll put the minus sign down here. So such a matrix is an orthogonal matrix because its 2 rows are both unit vectors and they're orthogonal. A rational alternative is 1 over 1 plus t squared, 1 minus t squared, 2t minus 2t, 1 minus t squared. Because we're just using the rational parameterization instead of the cosine sine parameterization. So here we stay within rational mathematics. Here we sort of have an approximate aspect, because if you actually want to calculate one of these things accurately, you need an infinite amount of time. All right, so those are orthogonal matrices. So how do we apply them to understanding a quadratic form? Well, the idea is to change variables. So diagonalizing a quadratic form means so we start with a 2 by 2 symmetric matrix. And what we do is we try to find an orthogonal matrix M such that when we transform it by this process of multiplying by M on one side and M transpose on the other, that we end up with a diagonal matrix. Okay, but if M is an orthogonal matrix, this is the same as saying that M inverse equals D, if M is orthogonal. And so the problem of diagonalizing a quadratic form with an orthogonal matrix is really the same as diagonalizing the matrix A in the usual linear algebra sense of diagonalization. This is the usual diagonalization procedure that you learn in first year, which involves the eigenvalues and eigenvectors of the matrix A. So I remind you, M is made up of the eigenvalues and eigenvectors of A. So we have to say a little bit about eigenvectors and eigenvalues of 2x2 symmetric matrices. All right, so the general problem of finding eigenvalues and eigenvectors of a matrix is, of course, a key problem in linear algebra. And it's generally very difficult to find such things completely, but we have to use numerical methods. In the 2x2 case, things are, of course, much simpler. But if we're talking about symmetric matrices, then a lot of additional information is known. Okay, so the theory of eigenvalues and eigenvectors for symmetric matrices is in many ways much simpler than for general matrices. And we can see that in the case of a 2x2 symmetric matrix directly. So let's have a look at the matrix A that we're starting with, A, B, B, C. And let's see what it looks like if we try to find the eigenvalues and the eigenvectors. So the characteristic polynomial of this thing is determinant of A minus lambda I, and we need to set that equal to 0 for the eigenvalues. All right, so that's the equation, determinant of A minus lambda, B, B, C minus lambda equals. So we have A minus lambda times C minus lambda minus B squared. And what is that? That's lambda squared minus lambda times A plus C minus, let's say plus AC minus B squared. Which I hope we all recognize, right? The general situation is it's lambda squared minus lambda times the trace of the matrix. Trace is the sum of the diagonal entries. And plus AC minus B squared is just the determinant of the matrix. That's the characteristic polynomial of a 2x2. Now, hopefully, we're going to be able to factor that and find eigenvalues. Right, that's the idea. We have to set that equal to 0 and solve for lambda. So can we do that? What happens when we try to solve this quadratic equation? So maybe I'll set this equal to 0 because that's what we're interested in doing. And we'll call this equation, say, star. All right, so star has solutions precisely when its discriminant is positive. So what's the discriminant? So the discriminant is, of this equation, is the b squared minus 4ac as a quadratic equation. Okay. So there's a b squared, that'll be a plus c squared, minus 4ac, so I guess it'll just be times ac minus b squared. And then if we stare at this, well, here's an a squared plus c squared plus 2ac, and here's a minus 4ac. So altogether that makes a minus c squared. And then we have plus 4b squared. So we get a sum of squares. It's a rather special situation. So in particular, this is always greater than or equal to 0. So approximately, we can always find solutions. From my point of view, I'm only interested in rational solutions, so I can say this is always a positive number, and that means approximately I can always find rational solutions. If it's a perfect square, well, then I get a complete perfect solution. But otherwise, there's still just solutions, which are approximate. And when do we actually get 0? When do we get equal roots? We get 0 only when both of these quantities are themselves 0. So we get equal, or get equal eigenvalues only if A equals C and B equals 0. In other words, when we are starting with a matrix which is a multiple of the identity. So if we have a symmetric matrix which is not a multiple of the identity, so therefore if A is a 2 by 2 symmetric matrix, and A is not equal to lambda times the identity, then we can deduce that A has 2 distinct, approximately rational eigenvalues. In other words, we don't have to go to the complex numbers. We can just stay over the real field, if you believe in such things, or in the approximate rational field. So that's an important property of the 2 by 2 symmetric matrices. And there's one other important property. The other fact is, I'll write as a lemma, that the eigenvectors of a 2 by 2 symmetric matrix A are orthogonal. Well, actually, the argument is valid for an n by n symmetric matrix just as well. And we'll assume that A is not equal to a multiple of the identity. And the proof is that, well, if A is not equal to a multiple of the identity, then then we have eigenvectors, say V1 corresponding to some lambda 1, and V2 corresponding to some eigenvalue lambda 2. Then we look at V1 times A times V2 transpose. So V1 is an eigenvector for A, so that means it's equal to lambda 1 times V1 A V2 transpose. On the other hand, this is also equal to V1 times V2 A transpose, since A is symmetric. And V2 times A is also, this is also an eigenvector corresponding to lambda 2. So this is lambda 2 times V1 A V2 transpose. And so now we're assuming that lambda 1 is not equal to lambda 2. Well, we said that we have unique eigenvalues. That implies that this quantity here has to be 0. V1 A V2 transpose equals 0. No, that's not correct. So my argument's not correct.
There should be a V1.
There should not be any A here. So V1 times A is just lambda 1 times V1. So there cannot be an A there. And but I can take this thing here and rewrite it like this. And then when I write A times V2, that's an eigenvector, so it's lambda 2 times V2, and the A again disappears. Sorry about that. So the conclusion is that we have lambda 1 times this is really the dot product, equals lambda 2 times the same thing, and that tells us that the dot product, or the dot product between V1 and V2 has to be 0. This thing has to be 0 if they're equal and these lambda 1s and lambda 2s are distinct. That's telling us that V1 is perpendicular to V2. And I guess the final thing that I should mention about this idea of changing basis is that when we change basis, when we perform this orthogonal change of coordinates, the characteristic polynomial does not change. So since M transpose equals M inverse if M is orthogonal, the characteristic polynomial of M transpose is the same as the characteristic polynomial of simply A. And that means, in particular, because the coefficients of the characteristic polynomial are just the trace and the determinant, it means that the trace and the determinant don't change. Under such an orthogonal change, under an orthogonal coordinate change. So that means if we have some matrix A, which is symmetric, A, B, B, C, then the two really important numbers associated with this matrix, or with the associated quadratic form, are the determinant, which is AC minus B squared, and the trace, which is A plus C. And these are going to be the two curvatures that we associate to the corresponding paraboloid. Okay? These will be the curvatures of the associated paraboloid. All right, so that was quite algebraic. Hopefully most of it was a bit of a review. So you've taken linear algebra, you've seen symmetric matrices, diagonalization of symmetric matrices by orthogonal matrices, probably already in the context of conic sections or quadratics. So I hope it's something of a review. Let's go back now in the last few minutes just to a geometrical view of these kinds of paraboloids. So something like, say, ax squared plus by squared, if I can rewrite it like this. So the associated matrix will be like this. So suppose that, for the sake of argument, we have something like x squared plus 2y squared. So the associated matrix is 1, 2, 0, 0. This is going to be an ellipsoid with elliptical cross-section, elliptic paraboloid. With an elliptic cross-section. This cross-section is kind of important. So the z equals 1 cross-section is, well, actually sometimes 1 or plus or minus 1, depending on the thing, is called Dupin's indicatrix. Sounds like something out of Harry Potter. Indicatrix, I suppose. All right, so here is the z. Here is z equals 1. So we're looking again at this familiar z equals 1 plane and looking where does the paraboloid meet that z equals 1 plane. Well, it does so along this conic. So there's, and that conic in the plane is called the Dupin's indicatrix. It's some kind of picture or representation of the paraboloid. If we have one that's a hyperbolic paraboloid, it's somewhat more interesting. So suppose we have, say, x squared minus y squared. Well then, okay, if z equals 1 and z equals minus 1, we can expect slightly different Dupin's indicatrixes. So if we have 1 equals x squared minus y squared, that's going to be a hyperboloid that, it's going to be a hyperbola that opens up. So there's the axes. The asymptotes will be like this. So when y is 0, x is 1. So there'll be maybe something like this in this direction. But if we have minus 1, we have x squared minus y squared, then we're talking about the intersection with the plane down here. Also an x and a y. And then the asymptotes like this, and the parabola, the intersection being hyperbola is opening in the other direction. So corresponding to our saddle shape. Oh, in this plane here, we have the two hyperbolas opening in this direction, down below the origin, which is the, so the center of the thing, down below they're opening up in a different direction. So these are the Dupin's indicatrices. There's sort of two of them in this case here. All right, so next time we're going to have a look more at the geometry of these quadratics. So one of the interesting facts about these hyperbolic paraboloids is that they're ruled surfaces. The elliptic ones aren't, but the hyperbolic ones are. And a lot of the richness of differential geometry comes about by the fact that when we're estimating surfaces, we have to consider not just, oh, maybe here's the easiest one. If you're approximating this surface at this point here, then in this direction it bends this way, and in this direction it bends this way. So right at this point here, the approximating quadratic is an elliptic paraboloid. It's one that looks like this. On the other hand, if we're looking at a point, say, in there, Then near this point, the surface is going in this direction along here, but along this direction it's going up. So up in this direction, down in this direction. So if we're approximating the surface at this point by a quadratic thing, we're going to have to use a hyperbolic paraboloid. And they're a little bit harder to understand. They contribute negative curvature. Ultimately, when we are talking about these two kinds of curvature, this is going to be called Gaussian curvature, and this is going to be called mean curvature. The Gaussian curvature is negative at one of these points, but positive at one of these points. So these quadrics play a crucial role in approximating surfaces and also giving us technology for defining the objects of interest to like curvature. So next time we'll see you again.